So we'll go ahead and start talking about some of the quiz questions. I went through everybody's quizzes, read them all, even if I didn't put comments on yours necessarily. And anything that was directly related to the class, I made sure to either leave a comment on your quiz submission to answer your question directly, and then for the most part, I also pulled those out and we'll go through them to make sure everybody's on the same page about all this stuff. As well as, I won't always take as much time as I will today to go over questions, but just for fun's sake, and since I asked you all that personal stuff about, what kind of music you like and everything, figure it's only fair that I answer too. Plus, I get to talk about music then too, instead of just science. So if you took Chem 100 with me in the spring, you may notice that we're going over almost the same exact stuff now that we started with in spring. The difference is that we're doing it at a deeper level, and we're going to be using it a lot more math heavy way. We went over concepts like uncertainty and sig figs and conversions, but there's a much higher standard as far as learning how to apply them to everyday life and keeping your sig figs straight and stuff like that. So initially, at least for Chem 101, it's going to be very similar to Chem 100, just at a deeper level. And then when we get into 102, 103, things start being a little different. We stop talking about things like theoretical yield and start talking about things like equilibrium, because it turns out no reaction actually goes 100% to completion. We have ways of calculating that and figuring out how fast they'll get there too. But it takes some additional background before we can get there. So we'll start with basic chemistry stuff again, and then progress as we get going. If you have an emergency and cannot attend labs or lectures for an extended period of time, the ideal solution would be that you're able to make it to labs and lectures. But in a non-ideal world, if you can't make a lab for any reason, ideally let me know, but if you can't let me know, that's okay. At the very least, you can at least do the pre-lab and some of the analysis questions for half credit. The way I grade the labs, you get half your points for doing the pre-lab and all the calculations, and you get half your points for being there and physically taking the data and learning all the lab skills. So if you can't make it to a lab, you can still at least get half credit. And you do get to drop one assignment at the end of the quarter as well. It's actually already built in. So Canvas already automatically drops your lowest grade in the assignments category. So if you miss a lab and take a 0 on that lab, odds are that's going to be the one that gets dropped unless you miss more than one. And if you're going to miss more than one, if it's a long-term thing, if you break both legs and are stuck in bed rest for the next 2.5 months, we'll deal with that when that comes up. We'll kind of handle it on a case-by-case basis. So if for any reason you need additional accommodations when it comes to scheduling, or you're just not able to make 1 or 2 labs in a row, let me know and we'll see if we can work something out. This might not feel like it when we're all crammed in this room, but this is actually a pretty small Gen Chem. Usually we're up closer to 40 students at this point still, and we're only at about 25. So there is actually room to switch back and forth between lab sections as well, to some extent. There's a hard limit on the top end. We can't have more than a certain number of students in each lab section. So if you need to, for 1 week, switch to the Tuesday, Thursday instead of the Monday, Wednesday, or vice versa, let me know ahead of time, but that's definitely a possibility as well. So it's almost the same time slot, just Monday, Wednesday versus Tuesday, Thursday. Monday, Wednesday is 10:30 instead of 10, but that's also a possibility if you have work schedule issues or you get sick or something like that. All right. And then, feel free to check out the recordings. I don't think they're not good enough to take the place of actually being here, especially considering how so you might not know exactly what I'm talking about. But you do have those as a last resort if you can't be here for any reason. What advice would I give people struggling to figure out what to study? Well, that's kind of a two-sided question there. If you mean what to major in, you can always major in chemistry. But really, pick something that you enjoy doing, something that keeps you excited about going to class, and ideally something that has some job outlook on the other end of it. I mentioned that it's hard to find job as a chemist, but it's not that hard compared to, say, I won't pick on any other majors, but there are majors that it's harder to find a job. It's just hard for everybody to find a job these days. If you're talking about within a class, pay attention to what kind of examples the teacher does that I do. Pay attention to the questions that get asked on the homework assignments. That's almost always going to be very similar to the type of questions you'll see on a test. So if there's stuff in the textbook that we don't cover in lecture, it might show up on a test, but the odds are pretty low. And if it does show up, it'd be like part of one question, not going to be a huge chunk of the exam. So pay attention to lectures, pay attention to homework assignments, and you'll know what to study. Especially for this class, because I give you the practice test. I'll give you last year's midterm. And I don't change up the format. I barely change the material. I change numbers and maybe what specific compounds or reactions we're talking about. So you should have a really good idea of what the midterm is going to look like before you even sit down to it. Right? So it shouldn't come as a surprise. Other classes, that's not always an option. But you can still pay attention. If you listen to what the teacher says and read between the lines, which takes some practice, you can usually figure out what's going to be on the test. Besides just reading the textbook thoroughly, what else is there to do well in this class? I'm not going to go through and put individual links, but there's some really good YouTube channels for chemistry. Chemistry is actually where Khan Academy first started. Sal Khan was tutoring his niece from across the country in OChem. So Khan Academy is great for chemistry. Occasionally it's too in-depth and goes into stuff that's beyond what we need for this class. But for the most part, if you watch the Khan Academy videos on general chemistry, it's going to be pretty helpful if you're struggling to understand some concepts. There's also another guy whose name is Professor Dave. His channel is, I think, Professor Dave Explains. We've got a really catchy and somewhat annoying little jingle at the beginning of each of them, but he's a fun guy. It's like a mushroom. Sorry, I can't say fun guy without making that joke. It's a condition. But yeah, there's lots of good YouTube videos. There's good textbooks. There's lots of good, explanation stuff that's available for free online. If you need help sifting through any of that, or if you want specific recommendations on a specific topic, just let me know and I can give you some. Professor Dave's really good at doing the quantum side of things, but he doesn't do so good on, solution stoichiometry. For that one, go to Khan Academy or something like that. So just, ask and I'll try to point you in the right direction. Anything that's really relevant that I think is a really good resource that I've found, I'll share it with you. Will the midterm and final exam be taken on campus? Well, that's the idea. They're going to be closed book, closed note in a room. Maybe this room. I'm still not decided for sure. But yeah, it's going to be a regular exam. We're not going to go take them on Zoom or anything, or use Proctorio or anything like that, as much as we can avoid it. That said, if for some reason you have a scheduling issue for the date of the final exam and you can't be there, let me know ahead of time, and we can either set up, if you have a really good excuse, we can set up a time with the proctoring center in the library, and you could take it there, or we can work around your schedule and my schedule for you to take it early, or whatever we need to do. So if there's some reason that you have a scheduling issue, just let me know and we'll work with it. But yes, the plan is for them to be regular, in-person closed note tests. But again, no surprises. You'll know exactly what's on them ahead of time. There will be a chemistry tutor. We're in the process of getting Cody hired. Cody took the OChem sequence last year, but virtually, so he's sticking around to audit the OChem class just because he likes chemistry and wants to do all the labs. So he's going to be our Gen Chem tutor and our OChem tutor. We don't know what his hours are going to be yet, though. So when I know better idea what his schedule looks like, then we try to schedule some time around either before lecture or after lecture. Usually works best for you guys to go see him in the library. Somebody asked about the success rate of students getting an A in this class. I've said before, I would like to give all A's to everybody. That said, I very rarely have any C's. I have mostly B's and A's. If anybody doesn't pass this class, it's generally because they've turned in less than half the assignments. You turn in the assignments and you show up for the test and you show up for lecture, you're almost always going to get at least a B. Right? So be here, do the work, ask questions, be present. And if not, I won't guarantee an A, but that'll almost always get you to at least a B. Like I said, very few C's. And the people that fail are the ones that disappear or just never turn anything in. So don't be one of those people, and you'll be fine. Right? Beyond that, I don't know specific numbers. I won't give you a specific percentage. Other than the people that figure out how to pass my classes, generally, like I gave all A's and 1 B in OChem in spring quarter. Right? It's lower success rate in classes where you guys are still just getting to know me and how to take tests and how to take my tests specifically. But it's still a pretty high success rate. So don't drop without asking me. Talk to me before you want to drop, because it's possible you're not nearly as underwater as you think you are. It's possible that you're in a totally normal situation. Like, no. You get these 2 assignments turned in, even if they are late, and all of a sudden that D is a B. So don't panic and just drop the class if you start getting a little bit behind. You have until this Friday to drop with no record, and then you can withdraw after that if need be. But again, talk to me first, especially since a W doesn't look all that different than an F when you're applying for a transfer. So, there's not usually a whole lot of advantage to withdrawing once you pass the drop deadline. All right, some random stuff. What is something I believe is true because it's backed by science that others generally disagree with or think is not true? Nuclear energy. Nuclear energy is something that's been demonized for a really, really long time. It's actually should have been way more highly used when it came to transitioning to green energy. It's way better than burning fossil fuels for electricity. At this point, I don't think it'll ever get fully used to its potential because we're close enough to being able to switch to fully solar and wind and other green energy sources that I don't think, and nuclear power has about a 10-year lag. You have to start building a nuclear plant about 10 years before you need the power. And in 10 years, hopefully we're almost entirely on fully green energy like wind and solar. So it's probably not going to get ever used, but really, really could have helped for the 80s and 90s and 2000s if people weren't scared by the word nuclear. I think I talked a little bit about why I like being a chemistry professor. You guys have to sit there and listen to me talk about science. I enjoy that. My family thanks you for your sacrifice. Yeah, I just think it's fun. It's fun to talk about science. I thought I was going to be a high school science teacher, but then I have to deal with parents, and I have to deal with like the fact that you're not adults, and I have to take attendance and stuff like that. So I like college better. I still get to talk about science. I just get to deal with adults instead of teenagers. Nothing against teenagers, but it's easier if I don't have to deal with parents and things like that. Climate change. How do you talk to your kids about climate change? I threw this one in there before I got into a big argument with my mom in front of my son about climate change over the weekend. My parents are both very, very conservative. My dad's more receptive to understanding that, it's a scientific thing. It's really happening. My mom, not so much. So, try to be realistic with them as much as possible without scaring them. My kids are only 7 and 5, so I really don't want to get into the nitty-gritty of, all these displaced climate refugees are going to cause a lot of pressure politically and potentially wars over things like that, like elevation and resources and famine. And so I try not to get into that level of detail with them. It's not exactly bedtime story material. But at the same time, you kind of have to be realistic. If people are afraid to talk about what's actually happening, then that's how you get people not having conversations that need to happen. But it is a scary thing. And then my answers for music, movies, and books. I always have a hard time. I try to pick a different musical genres to put up there every time. So I put some links in there. Blackened blues is actually a term that it really only applies to one band. It's a band called Zeal and Ardor. It's black metal fused with black spirituals and blues from the Delta in the Mississippi Delta. That's really fun. Kind of, if you're into blues or black metal, I highly recommend it. Run the Jewels. You can't go wrong with Run the Jewels. I love Run the Jewels. And then I like alt country. I really, really hate pop country, but alternative country. There's good country in Nashville still. It's just not on the radio. Sturgill Simpson's one of my favorites. He has a really good cover of Nirvana's song In Bloom. If you have never listened to any country before, that's a good place to start if you know Nirvana, because you'll recognize the song, and it's really good. Movies, I especially like sci-fi, but really kind of the stuff that does science relatively well, at least. Annihilation was really cool, really trippy. If you haven't seen that one, that was really good. The book was really good too. This guy, Kim Stanley Robinson, one of my favorite authors, because he does the science right in science fiction. He wrote a whole series about terraforming Mars, but it's not written, it doesn't read like a textbook. Well, I mean, parts of it do, but some of the geology stuff about the geology of Mars is really cool, but it's really dry. No pun intended. But he lives on a housing co-op at UC Davis, actually. And he's a really, really cool guy. He's been writing, he wrote this book about Mars in '93. He wrote Red Mars. And he's way ahead of the time on a lot of stuff. And so he's got some really good sci-fi out there. Then other random stuff, I tend to go towards like the magical realism literature type stuff. I love Cormac McCarthy and Gabriel Garcia Marquez. Salman Rushdie's pretty good too. And this is a really good comic. It's only like six issues, so it's like 100 pages or so. It's sort of like a South American magical realism sort of genre, except done as a comic. Really cool, weird book. I like cool, weird stuff. All right, and one last thing. Why do we need to take chemistry if you're going in the medical field? Well, because medicine is chemistry. If you're prescribing medical or chemicals as a prescription, you need to know what those chemicals are and what they do and how they interact. You have to start at this level before you can understand things like enzyme kinetics and binding affinities and protein folding. Before you can understand that, you got to learn the basics. So you start here. And do you consider AI a life form? AI is a big question. Well, maybe we'll tackle that one another time. We'll talk about a little bit about AI. AI is really interesting. All right, and then I left this in. This was last year. That announcement about phosphine gas on Venus happened right around the start of the quarter last year. We found phosphine on Venus. Does not mean we found life on Venus. It is still really cool, though. It means maybe there's life on Venus. We just don't know yet. And that's really cool, too. All right, let's get into some conversions. Let's get into actually doing some work. We've switched gears back all the way to chemistry. So if we want to go from feet to inches, we did this one as an example the other day. But practice setting it up the right way. I know you know how to look at that and get to an answer. Practice writing it out the right way so that you can show your work, so that it gets easier for the trickier conversions. If we want to cancel out, or if we want to convert feet to anything else, our first step has got to be canceling out feet. We've got to start with that. So no matter what you have a big, long conversion sheet that's available. It'll be attached to the test. You'll never have to memorize any of those conversions that are on the test. And since I actually have access to the internet now, we can pull that up so I can show you what you're looking at. It's available on Canvas under the resources section. No, the other way.
Higher conversion factors.
So it's 2 pages of equations and conversion factors. I know it's hard to read at this point from where you are, but this is the one that's most of your conversion factors are right in this section right here. So any of the ones I'm not going to have you memorize any of this. This will be on every test that you take. Right, so I would get used to using this one rather than just Googling what's the conversion every time you need a conversion. I would get a printed copy of this and I'll print it for you in my office if you don't have a printer so that you know exactly where everything is on this sheet. That way when you get to the test, everything's right where you're used to being. You've already practiced with it and know exactly where to look for everything you need. If you get used to using some other conversion sheet and then when you get to the test and it's this one and you can't find, centimeters to inches, then, and that's wasted time, even if you do find it eventually, right? So out of all of these conversions that we have, if we're trying to convert feet to anything, we got to start by canceling feet out. So find a conversion that has feet, ideally one that goes straight from feet to inches. If you don't have a conversion that goes straight from feet to wherever you're trying to go, you might have to do it in multiple steps. But you're always going to start by canceling out feet. Jordan?
12 inches over 1 foot.
Yes. So you guys all know 12 inches is 1 foot. Setting it up properly is the way that tells you whether you're multiplying or dividing by 12. Right, so 1 foot on bottom, 12 inches on top. Feet cancels feet, we get inches, right? We get 64 in this case. Something really close to 64. How many sig figs are we going to keep?
3.
3. 12 is exact. So that's why I keep asking to remind you. And that conversion sheet has a little disclaimer at the top. Again, I don't expect you to be able to read that from the back there, but all conversions within the same system are exact, and all conversions between systems are approximate unless otherwise noted. Right? So if you're converting from metric to metric, you can assume that the conversion is going to be exact. If you're converting from imperial to imperial, you can assume it's exact. If you're going imperial to metric, it's almost always going to be approximate, with only one exception, which is centimeters to inches. And that one's marked on here specifically. Right? 1 inch equals 2.54 centimeters exact. Right? So the equation sheet will remind you to be paying attention to that. But for the most part, your conversions are going to be exact until we get into things like densities. So in this case, we wind up with something that winds up being 64.0, I believe.
63.96.
So 63.96, keeping 3 sig figs.
4.0.
Exactly. All right, so quick review, since we're already better than that for the most part, other than needing to pay attention to our sig figs. But remember, if you don't cancel out your units, you're gonna have a bad time. Always start. That'll give you a hint which direction you need to go to. Just by looking at where you're starting, that automatically limits how many possible conversions you can use, right? Because you have to use something that has feet in it. So if you pay attention to that, and then if we wanted to go further, if we want to go inches to centimeters, now we're looking for a conversion where we can cancel out inches and be left in centimeters. Right, so it's always just stacked up on top of each other. Make sure you cancel your inches out, or your units out. It's an older meme, but it checks out. South Park never goes out of style, right? I don't know, South Park was new when I was in middle school. It's kind of getting up there. It's almost as bad as The Simpsons these days. Is it even still on? I think they're still making new episodes, right?
Season 27 or something?
Yeah. All right, if we want to go inches to miles, we probably don't have a conversion on your conversion sheet that goes inches to miles.
Inches to feet to miles.
We have inches to feet, though, and we have feet to miles. So start by canceling out inches, and you just always want to get one step closer to your final desired unit. I'll give you guys a minute, and then I will work through this one.
You flip the chart.
Yes. And I don't know how to get rid of that little thing, but I can zoom in. I didn't think that through, now it's going to open. Adobe. All right, so if we want to go inches to miles, and this is usually the same way that I'm going to see if I can. All right, I'll just go back to the slides. Then we want to go inches to miles. And this is usually how we would set it up on a test too. On the test, on the conversion section, I'm going to give you a number and a unit, then say into something else. Just leave it at that, and then all you have to do is show your work. All right, so stay over on this side for the sake of that recording. If we're in inches, we have a conversion to go to feet to miles. So sometimes it can be helpful to work backwards from where you're trying to get. There aren't that many conversions for miles, right? There's a lot of conversions with inches, but not that many for miles. So if you know I have to end at miles, I know that feet's going to be something that I'm probably going to use to get there. So 5.33 e to the 6 inches. Remember, that's our shorthand for scientific notation. 12 inches, 1 foot. And the conversion we wanted was 5,280 feet is 1 mile. So really roughly 5 million, that's going to take us down to like 500,000 divided by 5,000, something around
84.
84, yeah, let's go with 100.
84.1 is what I got.
84.1
With sig figs.
with sig figs. That's exact, and so is that. So 3 sig figs at the beginning, 3 sig figs at the end. And one note about units also, especially units that have M in them, there's a lot of them. So be careful not to mix up things like meters and miles, right? So a unit that is just M, that's meters. MI is miles. MIN is minutes. Don't write miles when you mean minutes. And then you get into prefixes as well, then that adds a whole nother wrinkle because these metric prefixes modify an existing unit. CM for centimeters, MM for millimeters. But lowercase m is millimeters. Uppercase M followed by a lowercase m is megameters, which is 1,000,000 meters or 1,000 kilometers. So that's megameters. If you flip that, you actually get a unit of concentration. You get millimolar. Molar, we'll talk about later, is moles per liter. This is actually really commonly used in biology. They use solutions that are millimolar all the time. All you did was switch where the capitalization was versus millimeter. That's an I, not an E. Right, so capitalization on your units winds up making a difference. What?
So you said lowercase m is a meter?
Lowercase m as the base unit is meter. Lowercase m as a prefix is milli.
Okay.
And usually you can tell from context if it's being used as a prefix or not. And if it's on a test situation, you can always ask me, and the worst thing I'll do is say, I can't tell you. All right, so, and all of these prefixes as well, we'll practice using those later today as well, but they are also on the all right, on the, we'll just go back to using this, go away. Down below the conversions is a whole list of all of the prefixes and what their abbreviation is, how you say it, and what the multiplier is. And we'll talk about what that means later. But basically, you can put these prefixes in front of any existing unit. It doesn't have to be a metric unit. You can actually have nano inches or mega miles. Mega miles would be capital M, lowercase mi. It would be 1,000,000 miles. Right, so these prefixes apply to everything. They make it really useful to make new units when you don't have units that are appropriate for the size of whatever you're talking about. And nano inches would be lowercase n, lowercase I, lowercase n. It's not a super common one, but it's one that actually does show up in some places where engineers are required to still use inches, like in the US. They do measure things down to the nano inches occasionally. So not the 9-inch nails. That would be capital N, backwards. Or is it the last one that's backwards? I can't remember. All right. So with these prefixes, since we generally try to keep numbers that are, in that 1 to 10 range, maybe 1 to 100 range as much as possible, because that's how our brain thinks about numbers, we're going to use prefixes to do that. So why use, why say 10 to the 6th meters when you can say 1,000 kilometers, or even better, 1 megameter? You still might not know what a megameter looks like since that's not a common unit, but it makes it easier to see how the math is going to work out in your head. So otherwise, we wind up with things like using feet for how long your road trip is. Right? That would be silly. We don't want to measure your road trip in feet. If I tell you I went on a road trip this summer and we went 1.5 million inches, that's stupid. The first thing you do is try to convert that to miles, right?
Yeah, we know that part.
I slipped a decimal. We went 15,000 feet. No, 1.5 million feet. We went about 3,000 miles. We drove from here, the day after graduation, we drove from here to Seattle and spent 3 weeks in Seattle. And then we drove from Seattle to Minnesota, where my in-laws live, and spent 4 weeks in Minnesota, and then drove back. And then got evacuated 2 days later, and then drove back to Seattle and back again for that. So we put a lot of miles on the car this year. It's a lot of inches.
No.
All right, so this is just a whole bunch of practice with conversions. You can just do, they're all fairly simple. There's nothing that tricky about them, other than some of them have these prefixes. Right, and so I have the prefixes that are relevant for this one written. And these prefixes are tricky because there's usually more than one way you can write it. You can say 100 centimeters equals 1 meter, or you can say 0.01 meters equals 1 centimeter. They're both equally valid, but one of them usually makes more sense. Most of us like working with whole numbers rather than decimals, right? So for the most part, we'll try and stick to using conversions that reflect that. And again, I'm not going to assume for now that you have the conversion sheet printed, but anybody who wants a printed copy, I will give you a printed copy if you don't have a printer at home. I don't have them with me, so remind me later. For today's lecture, I have them all on the slides where they're needed. But just to make the point, 10 10 to the 3 meters, or 10 to the 3 milli something, that's what it's saying there. So milli anything, 1,000 milli anything is one of the original unit. I could just as easily divide both sides by 10 to the 3 and wind up with 1 milli whatever equals 10 to the minus 3 of the base unit. Mathematically, that's just as accurate. Just a little bit harder to think about. If I was going to say 0.001 meters equals 1 millimeter, most of us would rather flip that around. But mathematically, it doesn't make a bit of difference. A flipped around version would be 1 meter equals 10 to the 3 or 1,000 millimeters. Just about. So this, I left these blank intentionally to show that it's a prefix. But yeah, we filled that in with meters, but it could be inches, miles, whatever.
Oh, I thought that was something we had to fill out.
I did too when I first looked at it. That's why I started answering it the way I did.
Gotcha.
Yeah, I think that's it. I think that's something else, right? All right, so if we want to go centimeters to millimeters, there is a conversion to go straight from centimeters to millimeters that's exact, but if you don't know it off the top of your head, you could wind up really easily multiplying by 10 when you were supposed to divide by 10, or the other way around. So if you're not sure, or you can't carry the powers of 10 in your head and simplify these, it can be easier to go centimeters to meters, and then meters back to millimeters. Right, so you can say, okay, 10.0 centimeters, I know that there's for every 100 or 10 to the 2 centimeters, that's 1 meter. And then I can go one step backward, kind of, to go to millimeters, say 1 meter is 10 to the 3 millimeters. And those of you who are good at simplifying fractions and doing algebra in your head might look at that and say, well, those just cancel out, and you can just do 10 to the 3 over 10 to the 2, which decides further to just be 10 over 1. But you don't need to remember that if you just set it up like this. Right, so the net result is if I take this and say divide by 100, then multiply by 1,000, the net result is I took my original number and I multiplied by 10. But you don't need a sheet that has every single possible combination of prefixes. Go back to the base unit and then convert. So our answer here would just be 100, right? Three sig figs. Started with 3, these are exact. And if you really wanted to, you could write it as scientific notation. 1.00 times 10 to the 2 millimeters. All right, we won't go through all of these. Is anything different if we're not talking about distances, if we're talking about hours, or seconds to hours? You might go to a different section on your conversion sheet if you don't remember how to get from how many seconds are in a minute. But other than that, no, the logic's the same, the math's the same. And so 34.87 seconds, 60 seconds is 1 minute. 60 minutes is 1 hour. Hour is one where I'm not going to be picky about the letters because there's no other units that have H in them. Technically for hour it's just an H, but it's really common to see it abbreviated as HR in everyday life. Same with seconds. If you want to write seconds as SEC, that's fine too, but technically the SI is just S. Right.
Could you move the one that says inches to gallons?
Ah, I'm glad you asked. So it's not just inches, it's inches cubed, right, which is already a volume, and is on our conversion sheet as well, in the volume section. So 1 gallon is defined as 231 cubic inches, and I have no idea why it's that number, what the significance is of 231, but that's the definition. So that's actually, it looks weird, but it winds up being just a one-step conversion. It's 600 inches cubed, and for every 231 inches cubed is 1 gallon. So you get something around 2.5.
Well, I can tell you where the length of an inch comes from.
Where does the length of an inch come from?
It's the length of 3 barley corns.
That's actually interesting. I did not know that.
Then a foot is the size of an average man's foot. A yard is the size of an average man's belt. And then I can't remember what a mile is.
The real question is, do you know where Fahrenheit comes from? Where 0 and 100 Fahrenheit comes from?
No.
0 was the coldest temperature that Lord Fahrenheit could measure, and he did it by mixing ice and salt together. 0 Fahrenheit was the coldest he could make it. And 100 is the body temperature of a cow. He was a land-owning nobleman in
You make do with what
in
you
Renaissance England. So they used that as a measure of wealth. Rather, he could have made it like human body temperature, but clearly for Lord Fahrenheit, it was more important to know how healthy his cows were. So, all right, I'm not going to go through the rest of these that aren't too tricky unless there is demand for it. Any of these in particular you want to go through?
I just want to see how you write the answer for the seconds to hours.
For the seconds to hours? Okay, what do we get for a number?
I don't know if I did it right. I got 0.0096 or 97.
So exact and exact, right? So we're going to want 4 sig figs, and these don't count.
Oh, sorry. So then it would be 9686.
9686 hours. So you could write it like that if you wanted to, because then it's still obvious exactly where there's 4 sig figs and what is a sig fig and what isn't. Once you remember those don't count. If you want it in scientific notation, it would be 9.686 times 10 to the minus 123
That's right. Okay.
hours.
But either way you read it is technically correct.
Correct, yeah.
Kick.
All right. If we're doing things with longer conversions, there is actually just a straight ahead conversion for seconds to hours on the conversion sheet too. It's just 60 squared, right? 60 seconds in a minute and then 60 minutes in an hour. So 3,600 seconds is an hour. You could do it in one step if you had that one in front of you. You don't. Everybody knows seconds to minutes, minutes to hours, right? So leverage what you have in your head and you don't need the conversion sheet as much. When it comes to longer conversions, especially when you're trying to go between US and metric units, sometimes you either have to pay attention to your sig figs or you have to make it a really long conversion. You want to use only exact conversions to get from, say, kilometers to miles. You have to convert your kilometers all the way to centimeters. Then you can go centimeters to inches because that's exact. And then you can go from inches back to miles. If you want more than 4 sig figs, that's kind of what you have to do. Because usually if you look up a conversion for miles to kilometers, it's usually only 4 sig figs reported. So if you happen to have more sig figs than that, and you want to keep all of your sig figs, you have to go the long way. However, if you measure something and you get 5.21 miles, and you want to convert that to kilometers, well, I only have 3 sig figs there, right? In my conversion, I have a conversion that's got 4 sig figs. Even if it's not exact, that's still good enough. But if you want to use exact conversions, if you want to keep more sig figs, then you got to go the long way. So this one, you could just say 1 mile equals 1.609 kilometers, and you're done. If you had 5.0127 miles, and we want to keep all of those sig figs, we have to go the long way.
Good inches.
With exact numbers.
And then you can use all exact conversions, and you get to keep all 5 sig figs at the end. It's a pain. On the test, I will go ahead and tell you now, I'm going to make you do it once on the test. And usually I don't dictate which route you take as long as you watch your sig figs on it. If I give you 5 sig figs and you use this, your answer better only have 4 sig figs on it. Okay, to show me that you understand that's an approximate conversion. Dylan?
What's the conversion from kilometers to centimeters? Almost like.
You got kilometers to meters, meters to centimeters.
Okay.
So let's work through this, and we'll go miles all the way to inches, probably, depending on how much space we have, and then we'll go inches to kilometers.
Is kilometers to meters on here and I just can't see it? Or am I crazy?
Right there.
Oh.
So 1 mile is 5280
5280 feet.
feet, but you want, 5280.
So 1 mile on bottom, 5,280 feet. Make sure that mile cancels out, right? 1 foot,
12 inches.
12 inches.
And 2.54.
We do have space to get to centimeters here. 1 inch is 2.54 centimeters.
Gotcha.
That gives us an answer in centimeters. It's going to be a big number, right? We just converted 5 miles into centimeters, so it's going to be something we need to write in scientific notation. But then we can turn around and go centimeters to meters, meters to kilometers.
Which is times 10,000 from centimeters to kilometers.
You want to check that, because that's why we show our work. It's 100,000, right?
Oh yeah.
So don't slip a decimal place. When in doubt, show your work and plug it into the calculator. Let the calculator crank through the decimal places. So we get here, what do we get for an answer?
806,713 and some change. If you put that in scientific notation.
And we want 5 sig figs, right? So we could actually leave it just like this and wind up rounding at the end. We could just keep all of our decimal places for now, or all the way, keep 1 extra decimal place. Since we're not going to be doing any addition or subtraction, we know we're not switching our rule anywhere. Or, just to be consistent, 8.0672 times 10 to the 5. 10 to the 6 gets us the million, so 10 to the 5 is 100,000s. Centimeters. And then we can go centimeters to meters, so 8.0672 10 to the 5 centimeters.
And 100.
So yeah, 100 centimeters is 1 meter. And 1 meter, 1,000 meters is 1 kilometer. So we're going to wind up dividing by 10 to the 5. Basically, that's just going to cancel out. We'll wind up with 8.0672 kilometers when we divide by 10 to the 2 and then divide by 10 to the 3.
Michelle, is there a way that we could just, sorry, just because of like the process in which you did it, and I'm looking it up, it says like kilometers to centimeters and centimeters to inches. Since you have to go down to inches to get to centimeters, why not just start there and convert to miles? Does that make sense?
Well,
Why do you have to
because-
go all the way down to centimeters if you're just gonna go back up to inches?
Good question. Because sometimes you're limited by what you have to measure with. If you're measuring a distance with your odometer on your car, you can't measure inches with that, right?
Right.
If you're in a perfect world, you could pick whatever unit you wanted to start with. There would be no need for conversions whatsoever, right? You could just say, well, I want my distance in kilometers, therefore give it to me in kilometers. Sometimes we're constrained by the fact that we can only measure in certain units. We don't always get to pick the units we measure in.
Right, but I'm saying if you're going to kilometers to miles, couldn't you just go kilometers to inches and then they take those inches and push them up to miles? Because it's all just the same conversion?
There's any number of ways you could
Okay.
rearrange this.
Okay.
That where you basically what you wind up doing though is you wind up combining some of these.
Okay.
If you combine some of these, then you wind up with a conversion that's no longer exact. Because if I say 5280 feet times 12 times 2.54, I can get a conversion that's a direct conversion from miles to centimeters. It's only one step. But that's one more thing to memorize. Instead, I have these numbers all memorized. I don't know what the conversion is from miles to centimeters off the top of my head. And unless I keep every single decimal, it's no longer exact. All right, if we did just take this and use the shortcut, what do we get for an answer?
.65, 8.065.
Not exactly what we came up with here, right? Which is why, it's still really close to the same number. We're arguing over a very small percentage of the actual measurement. But if you went to the trouble to measure all these sig figs, think about the trouble that you would go to measure something out to that many decimal places when you're talking about miles, right? If you went to that much trouble to measure that, you don't want to round off one of those decimal points just because you were too lazy to do the conversions the exact way, right? So on the test, if you do it this way and you leave it with the right number of sig figs, that's still full credit. I have ways around that, usually by asking you to go from like kilometers to inches, so you still have to do a couple more steps after this, or from centimeters to miles. But you can, if you're going from miles to kilometers, you can do it this way, you just pay attention to your sig figs. All right. That's as good a spot as any to stop for a break. Let's come back at 5 after 2. And we will practice using measured numbers as conversion factors, like densities.
Crocheting. Right. Yeah. Yeah, totally. I made a sweater last year. It was my first time.
It's a lot of crocheting.
Yeah. Had a lot of free time last year.
That's true.
What were you gonna say? Yeah, totally. I tried knitting and I was just like, this is too like stuffy. Like I want to just be able to be like, oh, whoops, I messed up. Add a few more stitches in or whatever. Yeah. Are you gonna fill in all the gaps, or is it gonna be like a nut kind of thing? Oh, cool. It's like a decorative sweater. That'd be cool.
I know we still have a few minutes left, but if you are feeling refreshed and ready to get back at it, go ahead and give this a try, and then I'll go through it and the logic for it in a minute too. So again, this first one seems like something that you know how to do intuitively, right? You know how to get an answer out, but when it comes to showing your work, or why you are going to divide by 4.15, it can be helpful to know how to set this up. Dylan?
I'm wondering, because the problem gave us that $4.15 equals 1 gallon of gas, is that one of those, I forget what the actual term is, that significant digits, is that an infinite? Because it says that's what it is?
It's not exact.
That's,
So
okay,
and prices get tricky,
right.
but when it comes to percentages are always measured.
Right.
Percentages are never exact, and prices are not exact either.
Okay.
Which means currency has significant figures as
So
well.
it's only 3 significant.
It would only be 3 significant figures. There's a reason why that's not actually the price at the pump, right?
4.154 it could be.
Usually, or they
4.15 and
usually
9/10.
they always make it 9/10, right?
Yeah.
So $4.149 per gallon, right? They don't write it that way. They write it as, and then like a little tiny 9 over the side, hoping you don't notice. But they're absolutely paying attention to that. And that absolutely factors into the sig figs. So that means that you get 4 sig figs on your dollars per gallon, and if you actually wind up with they have a mismatch of sig figs at the pump, because usually if you buy more than 10 gallons of gas, they report it to 5 sig figs, but their price per gallon is only 4 sig figs. But that's why your total, usually most pumps will stop at $100, because that's when they trip over into your price, and you get to $100 and you go to pennies, that's when you switch over from 4 sig figs on your price, your total price, to 5 sig figs on your total price. So they pay attention to this, and that's why sometimes it's at $125 instead, is because that's still within the realm that the USDA will allow when it comes to standards. They will still certify that as being accurate, despite the fact it doesn't follow our normal rules for sig figs. But yeah, companies absolutely pay attention to that, to fractions of pennies. Office Space wasn't wrong. And I'll give you a hint, they're never rounding in your favor.
Yeah, watch your decimal points.
Yeah, they know about those decimal points, and they just keep them because very few people are going to raise a fuss about 0.3 of a penny. But if you do that to 1 billion people 100 times a year, all of a sudden you just made $10 million just by rounding down every time. So absolutely still applies. If we have $40, if we're given something that only has 3 sig figs, that means our gallons of gas, we should only keep 3 sig figs. We actually use it like this, and then dollars is a weird unit, right? Because we usually write it with the unit in front of the number instead of the back, which is annoying because that's not how we write any other units. So a lot of times you'll see it written as at the end like that. USD stands for United States dollars, or GBP for Great Britain pounds, things like that. And you can write this as a conversion then. For a while, this number was way too big during the pandemic when the price of gas dropped like crazy. Now it's about right again. Actually, now it's low. But the fact that we can say these two things are equal means it's a conversion. Okay. Sig fig note on this number. When you have a ratio like this or a price, you're always going to assume that 1/2 of that fraction is exact. So we're going to just, if we have 4 sig figs here, we're just going to treat this like it's exact. And then we get our sig figs from the other half of the conversion. And same for like 100%. If we have, I'll use 32% by mass. That's 2 sig figs. If we write that as a conversion, we say 32 grams equals 100 grams of food. We assume that the 100 is exact, and that that's our 2 sig figs. It's going to control our sig figs at the end, right? And we see that with speeds, we see that with densities. Anything that is a combined unit or a percentage is a conversion if you write it out right. And sometimes that gives you tips on how to solve a word problem, because if you write it out like this, grams per gram of food, all of a sudden that might give you a hint where to start your conversion to try and go from, how many pounds of food do you have to eat 75 grams of fat. Well, write it like this: grams of fat, grams of food. Now that's got conversion that you might be able to use, right? So it kind of hints that you might want to use that.
Don't you want to make it a ratio instead of an equality?
So when we actually do the math, yeah, we'll do that. We'll turn it into the conversion factor, which is that ratio, the fraction form. But it's the same. I use the term kind of interchangeably because to me this is a conversion factor. Inequality is a conversion factor. I just need to do some algebra first. And so if we wanted to show our work here, $40. And for every, we'll use this one since that's what was given. 4.15 US dollars is 1 gallon of gasoline. Again, you knew how to do that, how to get the right answer, but this is how you set it up and show your work.
Can we also set it up as an equality,
5.61.
like $40 per X amount of gallons equals $4.15 per 1 gallon?
You can set it up as a ratio and do what they call butterfly cross multiplication, whatever you called it in middle school where you first learned it. You could say X over $40 equals 1 gallon over $4.15. Mathematically, that's fine, and then you just solve for X. And the units will still work out that way. And mathematically, look what happens. If we want to solve for X, we need to multiply both sides by 40, right? And you get 40 on top and divided by 415, and dollars on top and bottom canceling out. It's exactly what we had here. The problem with taking this approach is it only works for one-step conversions. If you don't need to go more than one step, that's fine. If we then wanted to take this, if the question was how many liters of gas, Then we have to go gallons to liters on top of that, and it's less convenient. Yeah, that is the next part. What about liters? Well, now going gallons to liters, we go to our trusty conversion sheet that has a volume section on it and find what we have to work with. So we've got a couple. We've got liters to cubic meters, liters to cubic centimeters, liters to quarts. That gets us in between the two from imperial to metric, right? So if we can get gallons to quarts, then we could go quarts to liters. Grace?
So is everything on here that's exact labeled exact?
If it's between systems, so for instance, quarts is British, liters is metric, that's not an exact conversion. Everything that's metric to metric is exact, everything that's imperial to imperial is exact. And everything between these two is approximate.
Unless it says exact.
Unless it says, and there's really only one of them.
So does the 1 gallon of 4 quarts mean you only have 1 sig fixer?
No, because those are between the same system. Quarts, that's a definition, so that's exact. Then we have 5 sig figs to go from quarts to liters, and only 3 sig figs on our price. So we'll be okay using that, even though it's not an exact conversion.
36.5 liters.
Sounds about right. If you're looking for a good, we do measure things in volume a lot in real life. And so it's good to have sort of a back of your mind approximation. A quart is approximately a liter, right? So you know there's 4 quarts in a gallon, there's also approximately 4 liters in a gallon, really roughly. Also worth noting that a pint is really close to a half of a liter. And it's been said that that's one of the main reasons that Great Britain won't ever fully abandon the British units, is because then you would go from serving pints of beer, which are 537 milliliters, to serving 500 milliliters of beer. They would lose 37 milliliters of beer on every pour. And they don't like that. Nobody likes that, let's be real.
No, we're not standing for it.
Exactly. So, if we wrote it out, it would just be 1 gallon, 4 quarts, and 1.0567 quarts is 1 liter. Turns out there is an exact way we can get there, but it's really long and involves cubing some conversions. We can go from gallons to cubic inches, and cubic inches to cubic centimeters, and cubic centimeters to liters, which I think might be the next slide. All right. Here's another one that has a concentration unit.
So you said the answer is like around 36, right?
Yeah, 36 point.
49.
Yeah, 495, whatever.
Which one of those was not?
The quarts to liters.
So because our original was the 9.64, we have to keep 3 sig figs.
We're only going to keep 3 sig anyway, so using the approximate conversion is fine, because this is 5 sig figs. Percentages, it can be a little bit trickier to say what you're talking about when it comes to writing it as a conversion. For instance, if the ratio of magnesium ions in a water sample is 175 parts per million by mass, what the heck does that mean? Well, it's a lot. Parts per million, parts per billion are just like percentages, except it's not for every 100, it's for every million or for every billion. So if it says 175 parts per million, that means for every, and by mass, yeah, for every 10 to the 6 kilograms of water, it's 175 kilograms of magnesium. Right? Percentages, it's easier because we're used to thinking about percentages, right? But percent literally means for every 100. Per million means for every million. Why did I pick kilograms here? It doesn't matter.
That's what we're working with.
We've got 10 kilograms there, so it's convenient. Could I pick other mass units?
Could have done grams and then just converted that over to grams.
Could have been grams, could have been pounds even. As long as they're the same on both sides with these ratios, you can pick whatever units convenient. So for instance, if we had, I don't know, in some states in this country, they still sell beer at the grocery stores that's limited to being 3.2 alcohol by volume. So that would mean that's 3.2 ABV is how it's listed or labeled. That really means that that's by volume. So as long as we pick volume units, we can pick whatever volume units we want. We can say for every 100 gallons of beer is 3.2 gallons of alcohol. You could do it in milliliters if you wanted to, as long as it's the same on both sides. Right, so percentages, parts per million, parts per billion, anything that's a ratio like that, it might be a measured number, but it's still a conversion, which means you can use a conversion to solve a lot of word problems. The one thing to remember is that usually these kind of conversions are going to be measured numbers. So now we're not in the exact realm anymore. So densities like we did in lab, speeds, anything like that where you have a fractional unit.
Are we going to go over the answer to that?
Sure.
Yeah.
So we have kilograms written over there. We have our conversion written out as kilograms, which since we're given a unit of kilograms, that tells us it might be handy to make our conversion kilograms. And for the sake of sig figs, let's go ahead and give that sig figs since I did not. What's happening here? Oh, numlock is not turned on. There we go. So 10 points. So 2 sig figs on our kilograms of water.
So the first thing you wrote was just the ratio.
So that's this number here. So when you have a word problem, a lot, especially in this class, a lot of times you're going to have multiple numbers mixed in. A lot of the time, most of those numbers are going to be a conversion in some form. You just have to figure out how to write it. So that's what this 175 parts per million by mass is.
So basically, so the conversion would be 175 yada 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 over the 10 to the 6 equals 1.
Right, so 10 kilograms of water. And for every million kilograms of water, it's 175 kilograms of magnesium. So kilograms of water cancels out kilograms of water. I should have been more explicit here. You can always add descriptors to your units to make it clear what you're canceling out. This was 10 kilograms of water. Yes. Kilograms of water cancels kilograms of water. Our units that were left in are going to be kilograms of magnesium. So divide by a million, multiply by 175.
0.00165.
175. 1.75 times 10 to the minus, let's see, 10 to the minus 5. No, 10 to the minus 7, and then we're going to convert that into grams. Since the question asks how many grams of magnesium.
Why is it 10 to the minus 7?
That's kilograms.
I went the wrong way, 10 to the minus. 3.
Yeah.
4.
It was 3.
3.
It gets easy to slip a decimal when you're trying to do it in your head. Trust your calculator if you entered it properly. Right, and that's kilograms of magnesium. And then, since the question asks for grams, we're just going to go 1 kilogram equals 1,000 grams. Right, so setting them up, finding the conversions in a word problem, setting them up right so that you can cancel out what you want to cancel out is part of the trickiest part of this class, is figuring out how to interpret a word problem. As you guys saw in lab this week, trying to find, well, I have 2 different volumes in this word problem. What the heck is that all about? And then you have to go read the procedure, like, oh, it's a burette. I'm supposed to subtract the 2. So it's not always as simple as just, well, that's a volume unit, so I'm gonna do something with that. Sometimes you have to do like a difference of something. But trying to figure out how to interpret word problems winds up being a huge part of this class, and then almost always you can finish it off with doing a conversion. Right? So let's do one with some conversions we're going to make up. We're going to estimate conversions. Conversions are also super helpful for what are called back of the envelope calculations. Meaning you want an idea of very, very roughly what a number is. But you could be off by a factor. You don't want to be off by more than, say, a factor of 10. Well, if you want to do a back of the envelope calculation, a lot of times you wind up having to just estimate, make up a conversion in your head. So if you look up a serving of gummy bears and you see that one serving is 17 gummy bears and has 140 calories plus or minus 10 calories. If someone ate 2 handfuls of gummy bears, how many calories were consumed? Whose hands, right? We're starting from 2 handfuls and we need to get to calories. So we need a conversion for hands or handfuls to number of gummy bears. That's not something you could really look up, right? If you had a package of gummy bears, you could count it out. Oh, the first time I did it, it was 15 gummy bears, if you have small hands, or you don't like gummy bears. The second time, maybe it's 21. You average the 2 numbers or something like that. You could actually get a conversion that way for handfuls to gummy bears. I don't have any gummy bears on me, so we're just going to estimate it. I'm picturing gummy bears in my hands. So I cup it like this, and maybe 15 is about right. That means we can say 1 handful, we're making up a unit here, equals 15 bears. Now all of a sudden we can go from, okay, well I started with 2 handfuls, and 1 handful is 15 bears. And we want to get to calories. Well, for every 17 bears, that's 1 serving. Or you could go straight for 17 bears is 140 calories. Save yourself a step in some writing. But in the interest of showing explicitly where this all came from, now all of a sudden we just made up a conversion, but that allows us to answer a real world question, at least really roughly, to 2 sig figs anyway. How many sig figs is on this, do you suppose?
No, wait, 1.
The way it's written, it's 2. We're assuming 1 handful is exact. If you wanted to write it in scientific notation. Could I be off by 10 gummy bears?
I don't think so. You could be off by one or two.
Probably not. I could be off by 1 or 2. There's no way I can fit 25 gummy bears in my hand, in one hand, and call it a handful, right?
Like you
That's like a measuring cup full of gummy bears at that point. So if I can't be off by a whole 10, then we call it plus or minus 1. Maybe the uncertainty is a little bit higher than that in actuality. Maybe I could actually be off by 2 or 3, but definitely couldn't be off by a whole 10. So we'll call this 2 sig figs. So 30 bears, it's a little bit under 2 servings, so we get something like 250.
247.06.
And we're only keeping 2 sig figs because this conversion and this one are both 2 sig figs, because remember it says plus or minus 10 calories. 250. 2.5 times 10 to the 2. A bargain at twice the price.
Now, how much energy does it take to burn that many calories?
That makes that much energy. Calories is an energy unit. The tricky about it in the US though, with the capitalization, a calorie is defined as the energy that it takes to raise 1 gram of water 1 degree Celsius. But that's a lowercase calorie. A nutritional calorie is actually 1,000 of those. So 1 nutritional calorie is enough to raise a kilogram of water by 1 degree Celsius.
How much is that in gallons?
A kilogram is 1,000 grams, right? It's about 2 pounds of water. And so that's about, it's about a quart. No, sorry, it's about a quart. All right. So interestingly, in other more enlightened parts of the globe, they don't do that. They actually use a metric prefix. But for whatever reason, because prefixes are scary to Americans, we do that instead of that. You buy something, I think Mexico for the most part, all of Europe will have their nutritional facts labeled in kilocalories, not capital C calories. But they mean the same thing. I don't know why we cater to that, because if they just started labeling nutritional calories like this, people would get used to kilo and what it meant. But instead we do that, nobody has any idea. Until you take this class, right? All right, this also allows us to do, so one more example of some way we might want to estimate things for a back of the envelope calculation. What if I said, how many calories are in a bathtub of gummy bears?
You'd have to know how many handfuls are in a bathtub.
You have to know how many handfuls are in a bathtub. We have to do some more estimating, right? You say, well, say a bathtub is, I don't know, roughly 4 feet long by 2 feet by 2 feet. Really roughly, right? That gives us cubic feet. Then we need a conversion to figure out how many cubic feet one bear takes up, or how many cubic inches one bear takes up. We'd have to start getting creative with it. We can just kind of make stuff up.
Space left to the bear, what's their compression rate?
Yeah, we're going to leave off dealing with that when we're dealing with as much uncertainty as we already have just by estimating the bathtub size. We won't get that granular with it. But yes, there are still a lot of places where there's some room. Patty, did you have a question?
Yeah, can you do it by weight?
You could do it by weight. That would be one way to do it. If you said, well, I think I can estimate how much a gummy bear weighs, or what the package says for the weight of the gummy bears, and do it by packages of gummy bears. I think that I could put 1,000 packages of gummy bears in a bathtub, and every package is X grams. And every X grams is this many servings, and every serving is 140 calories. Right, so we can get kind of creative with it. It helps to pay attention to where your uncertainty is, though, still, and understand why we pay attention to the uncertainty. You have to know what assumptions you made were good and valid, or at least how much you can trust them. A less concrete example, as far as what we're used to thinking about visually, would be something like Estimating carbon monoxide poisoning. Let's say we have some concentration of carbon monoxide, 15.0 parts per million carbon monoxide. If the average human inhales half a liter of air per breath and takes 20 breaths per minute, how many milligrams of carbon monoxide does the average person inhale in an 8-hour period? That's got a lot of stuff to it, but every piece of it can be written as a conversion. If you have these, inhales 0.5 liters per air per breath. There's that keyword per. Per means it's a conversion. 1 breath equals 0.5 liters. We've got 15.0 parts per million. Doesn't say, but we can usually assume, if it doesn't say by volume, if it's a gas, we can assume it is by volume. So for every million liters, they're gonna have 15 liters of pure carbon monoxide. And so we can go from, so that's going to be a conversion. 0.5 liters of air per breath is a conversion. 20 breaths per minute is a conversion. That's going to allow us to go breaths to time. Then the question right here, in an 8-hour period, that's not part of the conversion. That stands out because it doesn't have per in it. It doesn't have any fractional units. It's not a ratio. That's an absolute number. It's just a time. That's where we're going to start. You can figure out how many total breaths somebody takes in 8 hours. Then you can go breaths to liters. And then you can go liters to, actually, this one does say, gives us a density in grams per liter. So this is going to be parts per million by mass.
Could you do the whole conversion first and then do the carbon?
Milligrams. We're trying to get to milligrams. So here's our problem statement. 8.0 hours to milligrams of carbon inhaled, of carbon monoxide inhaled. That's what we're trying to do. So if we want to start planning out how to do that, well, we've got some conversions that go from hours to liters. We can go from hours to liters, right?
Yeah.
Hours to breaths, hours to minutes to breaths. And then we can go breaths to liters. That's liters of air, right?
Liters of air.
Liters of air. Now we can use this. Liters of air to liters of carbon monoxide, CO. It's given, we can use this as our conversion to get from liters of air to liters of carbon monoxide. Once we're in liters of carbon monoxide, we can use this to get to grams.
So 1 liter of air equals 15.0, whatever.
1 million liters of air equals 15 liters of carbon monoxide. It's parts per million, ppm. Sorry, I did not call that out specifically because I assumed you guys all knew what ppm meant. ppm means parts per million. So it's like a ratio, just like a percentage. Right, so without even filling in any of the numbers, this kind of gives us an idea. This is what we call a roadmap. I'm not doing any of the math yet. I'm just trying to say, well, I know I can do this conversion. I know I can do this conversion. And I know I can go, then I can use the density to go to grams to milligrams. And you can start filling in pieces here. Like, oh, here's where I'm going to use the density. Here's where I'm going to use hours to breaths is where I'm going to use the 20 breaths per minute. Right? So when you put it all together, you get one giant conversion if you want, or you can break it up into chunks. Let's start with hours to liters of air.
Are we going to plug in 8 hours?
We're starting with 8 hours.
8 hours, 60 minutes over an hour.
And we've got this conversion here, breaths per minute. So we want hours to minutes, and then we can get to breaths.
60 over 1.
1 hour
Is
60 minutes, good.
20 reps over 1 minute?
20 breaths per minute. So 1 minute is 20 breaths.
And then 25
That's a weird unit now, right? So if you're not sure where to go from there, look back here. We don't have any conversions on our conversion sheet that have breaths involved, right? So that's a clue that you either need to estimate something or check the word problem again.
And then per one breath, you take in 0.5 liters of air.
0.5 liters per breath.
That's like 1 breath.
So 1 breath equals 0.5 liters of air.
0.50.
0.50, thank you.
6
Exactly.
Just call that out. Sig figs.
It's also not explicit how many breaths, how many sig figs here, but we can assume they're not off by 10, right? So ideally, they should have put a point there to make it obvious, and that means, and then we can actually look at this and say, well, all of these measured numbers in here are 2 sig figs. So we're probably just going to wind up with 2 sig figs at the end. And we don't need to be quite as worried about in the middle, but I'll absolutely pay attention to it.
So you stop there to solve.
Just so I don't run out of room.
Right?
Yeah.
Okay.
Mathematically, there's no reason why I have to stop there. But it's a convenient place before I go to that second half of that problem. So what do we get? 120, 60 times 8, 480?
4,800.
4,800?
Half of 20 is 10, 10 to 60 is 600 times 8.
Yeah.
4,800.
I just
Would it
like the
be-
decimal. It's not 408? Yeah, no, that's right. Yeah. So this is liters, it's subscript air. So I can keep track of volume air versus volume of carbon monoxide.
And it's in 8 hours.
Because this is for 8 hours, this is how many liters of air you breathe on average. Us being at altitude, maybe this isn't a good approximation, or maybe this isn't a good approximation. We might take bigger breaths and more of them being at altitude. But that's nitpicking, right? So if we were measuring this ourselves, we could all go through and time how many breaths we took in 1 minute, and then make our own numbers if we wanted to, that were applicable to at altitude. All right, so once we're in liters of air, it can be helpful to come back here and say, okay, wait, I got the liters of air. Why do I care about that? Where am I trying to go? I'm trying to get to milligrams of carbon monoxide. So I've got to do something that's going to turn liters of air into monoxide, for starters, carbon monoxide, and get from a volume to grams. All right, so liters of air to liters of carbon monoxide, that's not something we're going to look up. That's got to be in the problem, or we don't know what to do with it. All right, so 4,800 liters of air, and for every million liters of air, it's 15.0 liters of carbon monoxide. Now we're in carbon monoxide, we're trying to get to mass, and we're in volume. Anytime you're in mass and you want to get to volume, or you're in volume and you want to get to mass, use a density, right? And we're given a density here, 1.2 grams per liter. So for every 1 liter of CO, it's 1.2 grams. We're almost there now. Last step was, again, go back and remind yourself where we're trying to end up. We're trying to end in milligrams, not regular grams. So tag one more conversion onto the end. 1 gram is 1,000 milligrams. And it's okay if you don't have that one memorized, that's on your conversion sheet. You just have to know that a milligram is smaller than a gram. And then you can check your conversion sheet and it'll remind you that the multiplier is 10 to the 3. So now we can do this and work all the way through it.
8.64.
8 point or 3 point?
8 point. I got maybe I'm wrong.
No, I just couldn't hear.
86.4.
86.4. And only 2 sig figs though, right?
I guess
So it's
86.
86 milligrams of carbon monoxide.
So it's only 2 milligrams. Oh, 1.2. Okay.
Yes, because there's 2 sig figs there, it's 2 sig figs there. That 20 breaths is probably 2 sig figs. All right, so that was really tricky, right? But if we start by just saying, well, I know where to start. If you can figure out what you're starting from and start canceling stuff out. Well, I'm in hours. I've got this random conversion of breaths per minute. So I could start by getting from hours to minutes. If you look at the tools you have in the problem or on your conversion sheet, and you start by canceling stuff out. Sometimes you can start to see where something's going to happen. Sometimes it helps to work backwards. For instance, if I looked at this and say, how many milligrams? Okay, good. I'm trying to get to milligrams of carbon monoxide. Well, nothing in here says milligrams, right? So before I can get to milligrams, I know I've got to get to grams. Then you look in here to see if there's anything that has grams. Oh, look, there's a density that has grams. So if you start at the end, milligrams to grams, then I've got a density. I can go liters to grams. Then look at this, and these parts per million in ratios a lot of times would be the hardest because they don't have the units explicitly laid out on them. But if you can look at this and say, okay, well, it's a concentration, it's a ratio. This is probably the single hardest one to actually see until you get used to doing this. And so if that one, the 15 parts per million is what where you got hung up or where you got stuck, that's fine. We'll keep working with it.
So, because that wasn't very intuitive for me to start with the 8 hour. Like for me, I would want to go straight to what I'm trying to find and start there. So I would have started with the milligrams to grams and then is that
And-
okay?
Yeah.
Okay.
So if you work backwards, if you can connect the pieces, it doesn't matter which side you start from. As you get more and more experience with these, you start to see patterns. Like, oh, like as soon as I start reading this, I'm like, well, okay, I'm going to be doing something with breaths and minutes, and that tells. I don't know exactly where it's going to fit in, but I know that I've got time involved and I'm going to breaths. Right. So once you start seeing some similar patterns, that gets a little bit more intuitive. But even I didn't look at this and immediately know what the order was going to be. Go one conversion at a time, backwards or forwards, until you can figure out how everything's going to work. Right? And as long as your units cancel out to give you the units that you want to end with, you probably did it right. Does this seem like, first off, does this seem like a reasonable volume for 8 hours of breathing?
Yeah.
I mean, I don't have anything that says it's unreasonable. It's not like I'm coming up with 1 billion, right? Or it's not like I'm coming up with less than a liter, right? So there's no red flags there. You can always stop if you seem like you're going too far, or I'm not sure if I was allowed to do that. If you did something wrong, a lot of times this number is not going to make any sense. Like if you divided by 60 when you're supposed to multiply by 60, you're going to get 10 liters or something like that. So that doesn't make any sense. I know what 10 liters look like, and I know that you breathe more than that in 8 hours. Right, so doing some reasonableness checks as you go can be really helpful while you're building up your confidence with these. All right, let's stop there for today. We'll end a few minutes early. Don't thank me too much because I'm sure I will make it up by being late on other times. We'll finish up lab tomorrow or Thursday, depending on your lab section. And then on Thursday for lecture, we will keep going and start talking about more ways we can use conversions.
Yay.
Do you have a few minutes after class? Just to-
Yes, I actually have office hours right now. If anybody wants to ask questions or go over more stuff, feel free to hang around, or if we stick around for too long and there's another class, I'll move us down to the last topic. Yeah, what's up?
I'm just trying to get that Excel
Oh, yeah.
whole thing done. I wasn't never able to get into Excel, but I was able to figure out how to go from text and columns on Google spreadsheets.
Okay.
I'm just wondering about the last couple of steps of that whole that sheet, so I'll just get into it now.
Yeah. Let me shut down the
Your book?
recording real quick.
What do you think?
So I'm on the same boat as